Hello students, welcome to Sri Jayendra's Ring Zone classes. I am your friend and mentor for coming classes with respect to physics. This is lecture number 9 of our unit work, power and energy. So let's begin with today's class. In today's class, we are going to discuss about the collisions. So let's begin with the collisions. What collision is? We can say that collision is an isolated event in which a strong force acts between two or more bodies for a short interval of time, as a result of which the energy and momentum of the interacting particle changes. So when we say that there are certain internal forces could be there due to which a certain amount of force is going to be acted on the bodies, and due to which their energy or momentum or energy and momentum both could be changing. So we can say during the collisions, there will be an exchange of momentum between the bodies, and the kinetic energy of the body may remain constant or it could be changed. Accordingly, the collisions can be classified into two kinds. So we can divide this into two different sections. One is the elastic collision and another is the inelastic collision. Now we have different approach to classify the collisions. They are based on the basis of conservation of kinetic energy. So on the basis of conservation of kinetic energy, we have two collision. First, it is the elastic collision, in which both momentum and kinetic energy are conserved in elastic collision. So momentum is conserved, kinetic energy is conserved when we talk about the elastic collision. I hope this is clear. Next is the perfectly elastic collision. In this collision, kinetic energy after collision is equals to kinetic energy before collision. The collision is said to be perfectly elastic, such as the collision between atomic particles are there, or we can say it's a bouncing off ball with same velocity after the collision with the earth. The situation is something like this, that let's suppose this is the object, and let's suppose we have dropped it from here. It is going to be collide with the earth surface over here, and again going to rebound to the same height. This is the case when it is rebounding after collision. So this is the cases of perfectly elastic collisions. Next, inelastic collisions. So it is the collision in which only momentum is conserved but not kinetic energy, is called as the inelastic collision. So it is the case where momentum is going to conserve for sure, but kinetic energy is not going to conserve at all. So it is the case of the collision between two automobiles on a road. In fact, all majority of the collisions belongs to this category. So in practical life, we will be having, in most cases, it would be the inelastic collisions, because kinetic energy is not going to conserve anywhere, and certain other fractions of energy too is going to conserve. That let's suppose the situation would be something like this, that this is the first object, this is the second object, this is moving in this direction v1, this is going to move in this direction. Let's suppose their mass is r m1 and m2. They are going to collide, suppose at this instant, and then they are going to be move in this direction v2 dash, this is v1 dash. Again, it's a mass m1, it's a mass m2 in this direction. So the thing is, when they are going to collide, there are certain other energies too can be developed, such as light energy, or we can say it's a sound energy. Yes. So in this kind of energy, or major, it would be an heat energy. So in this kind of energies, your energy is going to be wasted, and that's why the initial kinetic energy, let's say it's in half m1 v1 square plus half m2 v2 square. This could not be equals to half m1 v1 dash square plus half m2 v2 dash whole square. I hope this is clear. So in most cases, when and when we have seen a certain accidents even, so there would be a certain kind of sound has been developed, there would be a certain heat has been developed, and due to this reason your energies cannot be being conserved. So in most of the practical lab, it would be the cases of inelastic collision. I hope this is clear. Yes. Now perfectly inelastic collision. So if in a collision two bodies stick together or move with the same velocity, then after the collision is said to be perfectly inelastic. Let's suppose a case is that, suppose this is wooden block and a bullet is there. Bullet is moving in this direction. It is going to hit the wooden block, and after that after that wooden block plus bullet is moving with certain velocity v dash. Let's assume that this is m into v and this is m. So at this point of time we don't know what final velocity or what should be the combined velocity of this two objects. But this is a kind of a perfectly inelastic collision where two bodies stick together, and when they are stick together, it is obvious that they are going to move with the same velocity. This is what we call as a perfectly inelastic collision. So this is the one of the approach. This is the one of the approach through which we can classify the different collisions. Now let's look at the another approach. It's on the basis of the direction of colliding bodies. So in this case, it is the basis of the direction of the colliding bodies. Let's look at that. The first is the head-on or one-dimensional collision. Head-on collision or one-dimensional collision. So it is the collision. It is a collision if the motion of colliding particles before and after the collision is along the same line, then the collision is said to be head-on or one-dimensional. Yes, mostly it is the cases we are going to discuss on. Yes, it is our part of the syllabus. Primarily, yes, again primarily. Yes, because NCERT has derived this and NCERT has written a certain cases as well. So mostly we are going to discuss this, that when two particles are going to collide before it and even after the collision they are along the same line, then this could be said as a head-on collision or one-dimensional collision. This is oblique collision. So if two particle collision is glancing, such we can say that such that the directions of motion after collision are not along the initial line of motion, then the collision is said to be as an oblique collision. If it is in oblique collision, if in oblique collision the particle before and after collision are in same plane, the collision is said to be two-dimensional. Otherwise, it has been called as the three-dimensional. You can say collision of billiard balls. They are the oblique collisions. Yes, even if you have played the carom, yes, it is even the same case. Even it is the same case where initial collision and final collision, they are not on the same line. I hope this is clear. Yes, once we know this that this is the collision and this types of collision and all that kind of stuff, one more thing to clarify is that when we say the collision has been divided into two parts initially, one was the elastic collision. When we say that in this collision momentum and kinetic energy is being conserved. When we say this, that in elastic collision, during the case of the elastic collision, that momentum and kinetic energy is being conserved. When we say this we have one clarification, that let's suppose that this is mass m1, velocity u1, and moving in this direction. This is the mass m2, initial velocity u2, and moving in this direction. And let's say they are going to collide. And after that let's assume that this is m2, this is v2, and this is m1, this is v1. So once the situation would be something like this. So when they are colliding, momentum is conserved, that is for sure, every time, each time. Yes, whatever could be the collision, momentum is going to conserve. Now let's talk about the kinetic energy. So when elastic collision is there, look at this moment when they are colliding. There could be a certain change in shape could be there. So so kinetic energy kinetic energy is conserved over here. It is the kinetic energy, let's say initial. I can write it's a kinetic energy final. But at the time of collision, at the time of collision, kinetic energy is not going to conserve. Yes, I hope this is clear. Even in the elastic collision, I hope this is clear. Is it clear? So if I summarize this, that this is the elastic collision. Another one is the inelastic collision. So let's say about the momentum and kinetic energy. So when we say elastic collision, when we are talking about the momentum, it is going to be conserved. When we are saying about the inelastic collision, and when we are talking about the momentum, it is conserved. So momentum is always conserved. When we say about the kinetic energy, in the case of the elastic collision, then it is going to be conserved. But that is for before collision and after collision. And in this case, in elastic collision, when we say about the kinetic energy, it is not going to be conserved. It is not going to be conserved. I hope this is clear. Is it clear? Yes. Now any confusion? So when they ask, do the kinetic energy conserved in elastic collision, then we can specifically say that yes, kinetic energy is going to be conserved. But when we say this that kinetic energy is going to be conserved, we say for the before collision and after collision. If they want specifically at the time of collision, then kinetic energy is not going to conserved. I hope this is clear. Is it clear? Now any confusion? Is there anything? No? Great. So let's have certain questions based on this. It says that the quantities remaining constant in a collision are. So which are the quantities that remain the collision? It says momentum, kinetic energy, and temperature. Second option, it's a momentum, kinetic energy, but not the temperature. It says momentum and temperature, but not the kinetic energy. It's a momentum, but neither kinetic energy nor temperature. Now, what should be the option? Tell me. So, first thing what I need to look after is that they have mentioned collision. They have not mentioned elastic collision and inelastic collision. So, if it is the case of inelastic collision, kinetic energy is not going to be conserved. So, this is not the correct one. Even this is not momentum and kinetic energy, but not the temperature. No, momentum and temperature, but not the kinetic energy. We are not sure for this. Yes, we are not sure for this that temperature is not going to be changed, because it might possible that at the time of heating, at the time of colliding, a temperature may get changed. Yes, so this could be the best suitable answer, momentum, but neither kinetic energy nor temperature. I hope this is clear. Is it clear? Great. Now, second question. In an inelastic collision, the kinetic energy after collision. Yes, inelastic collision. Look at this. They are talking about the inelastic collision, the kinetic energy after the collision. First is same as before collision, so this could not be the answer. Is always less than that before collision. Is always greater than that before collision. Maybe less or greater. Yes, we cannot say 100% that it would be a greater than or it would be a less than that before the collision. I hope this is clear. Is it clear? Is it any doubts up till now? Is there anything? No? Great. So now let's begin with the one dimensional elastic collisions, and we are also going to cover their special cases. So let's have a look over this, and please be very careful. Let's have a look. It's a one dimensional elastic collision. So let's suppose that two spheres of masses m1 and m2 are moving with initial velocities u1 and u2, and they are moving in the same direction. Look at this, and they are going to collide such that their after collision their final velocities would be v1 and v2. So what we are supposed to do is, initially we are going to derive a formula. I'm sure that you must have gone through this and you have derived this formula at your school classes as well, but I'm doing this so that only the things can be revised quickly. So let's do it quickly and we will switch to the special cases. Yes, so we have two spheres, m1 u1, another sphere, its mass is m2, initial velocity is u2. They are going to be collide, and after collision they are moving with the v1 and v2 velocities. When we say collision, mostly we are going to discuss that u1 would be greater than u2, and v2 would be greater than v1. Yes, this was the case. This was the case, so that we are going to study it. Yes, why only this? Let's think and let me know that why u1 should be greater than u2, and why v2 should be greater than v1. u1 should be greater than u2 because this is the only possibility when they are going to collide. If a reverse is true, that means if u2 is greater than u1, then they are not going to collide anywhere. Think. Yes, am I clear? Yes, great. So u1 must be greater than u2, and in this case v2 would be greater than v1, so there would be no any multiple collision. If it was not the case, then there could be a chances of multiple collision. So to avoid that multiple collision, and we want that collision occurs only once, that's why we just want that v2 should be greater than v1. I hope this is clear. So let's derive it. So first thing what I understand is from the law of conservation of linear momentum. Momentum of the system before collision is equals to momentum of the system after the collision. So we have two objects, and this two objects, this make our system. So this is our system. Yes, so when we say momentum is going to be conserved, when we say momentum is going to be conserved, we always say that momentum of the system is being conserved. I hope this is very clear. Yes, so what I can understood is that initial momentum of the system should be equals to final momentum of the system. It could be something like this. So while I say so, I want to clarify one thing, that let's suppose the initial momentum of this is 40, initial momentum of this is 60, and So this total momentum of the system initially before collision it is 100. Now it might possible that afterwards the momentum of this becomes 20, and afterward the momentum of this becomes 80. So if you observe it very carefully, m1, or I can say momentum of m1 before collision and momentum of m1 after collision is completely changed. Same thing is true for the m2 object as well. So we cannot say that they are changing and they are going to keeping at the same. What we are assuming and what we have relations and what we are saying is the total momentum of the system initially it is 100, and the total momentum of the system would be 100. We cannot say that m1 u1 must be equals to m1 v1. No, this is not the momentum conservation. This is the incorrect one. I hope this is clear. When we say we are talking about the system only, so you need to first derive the boundary of your system. That means you need to decide that which all are the objects that can came in my system consideration. Once it has been defined, it will be very easy for you guys to to understand the situation clearly. I hope this is clear. Is it? Great. So we are talking about this, that m1 u1 plus m2 u2 must be is equals to m1 v1 plus m2 v2. So I can write like this. This is moving on this side and this is going to be moving this side. So this would be equals to m1 u1 minus m1 v1. That should be is equals to m2 v2 minus m2 u2. And when I write this, it's m1 into u1 minus v1. That should be is equals to m2 into v2 minus u2. So this is the first relation. Keep somewhere, keep it right in your book somewhere. Now we know that according to the law of conservation of kinetic energy, even we have one clarification that kinetic energy of the system before collision would be always equals to the kinetic energy of the system after collision. I can say so when I am talking about the elastic collision. I can say so when I am talking about the elastic collision. So in the elastic collision I can have the relation, it's an half m1 u1 square plus half m2 u2 square. That should be is equals to half m1 v1 square plus half m2 v2 square. When I say so, it's in half m1 u1 square. This is moving over here and this is moving over here. So it's in half m1 u1 square minus half m1 v1 square. That should be equals to half m2 v2 square minus half m2 u2 square. So this and this has been cancelled, and we can have it's an m1 into u1 square minus v1 square. That should be is equals to m2 into v2 square minus u2 square. This is my second relation. So let's just divide equation 2 by the equation 1. What I can have is it's a m1 into u1 square minus v1 square. That should be is equals to m2 into v2 square minus u2 square divided by m2 into v2 minus u2. So this could be cancelled out, and let's factorize this too. Then they can factorize at u1 plus v1 and u1 minus v1. Divide by u1 minus v1 is there, and this can be factorized as v2 plus u2 into v2 minus u2 divided by v2 minus u2. So this could be cancelled out. Once this could be cancelled out, we have this relation that u1 plus v1 is equals to v2 plus u2. From this we can have this, it is u1 minus u2. That should be equals to v2 minus v1. This is the relation number 3. And let's put this relation put the relation as the relative velocity of approach before collision is equals to the relative velocity of separation after collision. So velocity of approach, the situation was something like this. This was m1 moving in this direction with u1. This was m2 moving in this direction with velocity u2. At certain point they are going to collide, and then it is the m2 into v2 This is the m1 into v1. So when I say velocity of approach, when I say velocity of approach, it would be u1 minus of u2. And when I say velocity of separation, it would be v2 minus v1. So from this we have that velocity of separation and velocity of approach would be equal. So we can have that v2 minus of v1 is equals to u1 minus of u2. And from this I can have this relation, that v2 is equals to u1 minus u2 plus v1. Now let's just substitute this relation in equation number 1. And once I replace this with, what I can have is, it's an m1 into u1 minus v1, that would be equals to m2 u1 minus u2 plus v1 minus u2. And by simple mathematics, what I can have is that is equals to v1 is equals to this. While I say this, let's look at this. It's a v1 is equals to m1 minus m2 upon m1 plus m2 into u1 plus 2m2 divided by m1 plus m2 into u2. I hope this is clear. Is it clear? Is it? So please do remember this. This is very very important. It's a final velocity of the first object after collision. Now from the equation we can have the relation this two. It's a v1 is equals to v2 minus u1 plus u2. And we are going to substitute this value of v1 in equation 1. If we are going to substitute it, we would be having this relation, that it would be v2 is equals to 2m1 upon m1 plus m2 into u1 plus m2 minus m1 upon m1 plus m2 into u2. I hope this is clear. Is it clear? Is it clear? Any doubts in this? Is there anything? Is it there? So what relations we are having is, let's just summarize this, that it is m1 moving in this direction with u1, it is the m2 moving in this direction with u2. They are going to collide, and then onwards it's m2 which is having the final velocity of v2, and m1 v1. I hope this is clear. So when I write v1, it's a final velocity after collision. It's a final velocity after collision that could be given as, it's a m1 minus m2 divided by m1 plus m2 multiplied by u1 plus 2m1 divided by m1 plus m2. This should be 2m2. It's a 2m2 into u2. Yes. So this is the final velocity. This is the final velocity of first body. It is this. And let's understood what is v2. What is v2? Final velocity of second body. That would be equals to m2 minus m1 divided by m1 plus m2 into u2 plus 2m1 divided by m1 plus m2 multiplied by u1. Yes, look at these relations very carefully. These are the relations that needs to be remembered. These are the relations that needs to be remembered. And do you find any correlation between these two? Do you? Let's look at this. And this is just the approach so that you can remember it easily. Let's have a look. That when I say v1, when I say velocity, or I should say final velocity after collision, I begin with the m1, and here as well it is u1. So it's an m1 minus m2 divided by m1 plus m2 into u1. And once I have ended up with the first body information, I begin for the second body. It's a 2m2 divided by m1 plus m2 into u2. Same thing is true even here. It's a v2, final velocity of second body. So when here I was talking about the first body, I have begin with the m1. Here I am talking about the second body, so I will begin it with the m2. So this is m2 minus m1 divide by m1 plus m2. Once it was v1, this is u1, so this is v2, it is a u2. Now once the information about first body is over, you will switch to another body, that is of first body. For the second body, it's a 2m1 m2 divide by m1 plus m2 into u1. I hope this is clear, and this will help you guys to remember it. Is it clear? Is it is it clear? Are you sure? Are you sure? Any doubts up till now? Is there anything? Is there anything? Any doubts? Is there anything? No? So will you be able to do the questions based on this? Are you sure? Can we do it? So let's have a look. That let's suppose our first object is that this is m1, another object is that this is m2. This is moving with the 10 meter per second, this is moving with the 20 meter per second. They are going to collide something like this, and let's say this is m2, this is v2, and this is m1, this is v1. So what they want is find out velocity v1 and v2 after collision. So do one thing. Have you written the formulas? Have you written it? Once when we discussed this, once we when we discussed it, did you written it? No? If not, please take your time of 30 seconds and just write it down. But do it quickly. Write it down. Have you written it? Have you? Have you written it? Are you sure? Great. So now let's put up the value and get the answers done. Get the answers. So if you want that mass of the first body, it's a 1 kg, and this is 2 kg. What was your answer? Do you have v1 and v2? Do you? Do you have v1 and v2? Let me help you guys. Think it that do these bodies collide? Can this be collide? Can a collision is possible? Look at this. This is moving with 20 meter per second in this direction. This is moving in 10 meter per second in this direction. As u2 is greater than u1, these bodies are not going to collide anywhere at any time. I hope this is clear. So whatever the data that we have been given, these are not going to collide, and when they are not going to collide, this v2 would be having the same velocity, it's a 20 meter per second. This v1 would be having the same velocity, it's a 10 meter per second. I hope this is clear. Is it clear? Is it? Do you understand this? Do you understand that once when you apply a formula, these formulas are correct, you can always apply them, but once you apply it, please do remember that this was when we have written this, we have assumed that u1 must be greater than u2 and v2 must be greater than v1. Yes, we have assumed it and then we have derived it. I hope this is clear. Is it clear? Is it? So you can always apply a formula, but once you apply it, before applying to it, we must understood the basics. We must understand that what the concept was and when this formulas can be applied. Is it clear? Is it? Now let's work for the next question. Now they are going to collide for sure. So please do it. That this is first, second object, this is first object, this is of 1 kg, this is of 2 kg, this is moving with the speed of 10 meter per second, this is moving with the speed of 20 meter per second in the same direction. Now they are going to collide somewhere, and after the collision they are going to moving like this. It's a, let's say 2 kg body, it's a 1 kg body. What I want the final velocity of first body, final velocity of second body. So let's work for it. So what I assume is that v1 could be written as it's an m1 minus m2 divided by m1 plus m2 multiplied by u1 plus it's a 2m2 divided by m1 plus m2 into u2. So if I put up the value over here, it's an m1 minus m2. This is equals to, this is equals to 1 minus 2, it is a minus of 1 divided by m1 plus m2, it's a 3 multiplied by u1, this is equals to 20 plus 2 into m2, this is 2 into 2 divide by m1 plus m2, it's a 3 multiplied by, it's a u2, this is equals to 10. So this would be equals to minus of 20 by 3 plus 2 2s are 4, 4 10s are 40. So this is plus 40 by 3. This would be equals to plus 40 minus 20. So this would be a plus 20 by 3 meter per second. This is the final velocity v1. I hope this is clear. Is it clear? Is it? Now on a same note, I can have a v2 that is equals to m2 minus of m1 divide by m1 plus m2 into u2 plus 2m1 divide by m1 plus m2 into u1. So that would be equals to, if you remember, this second body is of 2 kg and first body is of 1 kg. This is moving with the 10 meter per second and this is moving with the 20 meter per second. So this is equals to 2 minus of 1 divide by 2 plus 1 3 multiplied by u2 initial velocity of second body, it's a 10 plus 2 into m1, so this is 2 into 1 divide by m1 plus m2 3 multiplied by u1, it's a 20 meter per second. So this is equals to 2 minus 1, it's a 1 by 3 into 10 plus 2 by 3 into 20. So this would be a 10 by 3 plus 22s are 40 by 3. This would be 10 plus 40, it's a 50 by 3 meter per second. I hope this is clear. Is it clear? So this was the v1, this was the v2. This is the final velocity after collision. Does it clear? Does it? Does it clear? Are you sure? Yes. Is it clear? Any issue, any concern over it? Anything? Do you have any queries? Do you? Do you have any queries over it? No? Okay, great. So let's discuss first a coefficient of restitution before we will switch to the special cases of the collision, because this is very important terminology. But this is very important terminology when we discuss the collision. So let's just discuss it and we will back to the special cases of elastic collision. So let's begin with the coefficient of restitution. What is it? The coefficient of restitution between two bodies in a collision is defined as the ratio of the relative velocity of separation after the collision to the relative velocity of approach before collision. So this is just the ratio which define as its a relative velocity of separation divide by relative velocity of approach. So if you want that this was first, this was second, this was moving with u1, this is moving with u2, they are going to collide, and after that this was v2, this was v1, this is moving in this direction, this is moving in this direction. So it's a velocity of approach, it's a velocity of approach that, and velocity of separation, this is what we can say velocity of approach, that with which velocity it is going to moving towards it, it's a u1 minus u2, and this is the v2 minus v1. This shows with which velocities they are going to be separated. Yes, so this is coefficient of restitution, which can be given as relative velocity of separation divided by relative velocity of approach. I hope this is clear. Is it? So the value of coefficient of restitution is independent of masses that we can observe and the velocities of the colliding bodies. It depends on the nature of colliding bodies. It depends on the nature of the colliding bodies. And for perfectly elastic collision, E is equals to 1. Perfectly inelastic collision, E equals to 0. When I say for perfectly elastic collision, E is equals to 1, I can say so for the elastic collision as well, that for the elastic collision E would be equals to 1. And for inelastic collisions, the value of E, that is lying between 0 to 1. I hope this is clear. So so for perfectly elastic collision, this E, its a coefficient of restitution, that would be equals to 1. So if you remember it very carefully, what was E? It is the velocity of separation, or I should say rather it's a relative velocity of separation. It would be a relative velocity of separation divided by relative velocity of approach. So this is equals to v2 minus of v1 divided by u1 minus of u2, and this is E. So for elastic collision we can have so that E is equals to 1. And when I say for elastic collision E is equals to 1, this is equals to v2 minus of v1 divided by u1 minus of u2. When I say so, that E is equals to 1, this is equals to u1 minus of u2, that is equals to v2 minus of v1, that we have used, if you remember it, that we have used this point, we have used this concept while we were deriving the relations for the final velocities, that when we derive the relation of v1 and v2, we have used this relation. I hope this is clear. Is it clear? Is there any issue? Now, do you understand what coefficient of restitution is? Are you clear with this? Are you any issue, any concern over it? Any doubts? Is there anything? Is there anything? 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 No? Great. So let's understood the first question with a different approach. That this was our first question. This was our first question. Have a diagram of this in your book, and we will do this. We will do this one more time, but with little different approach. Let's have a look. That 1 kg body 20 meter per second, 2 kg body 10 meter per second. Okay. So this was the case that it's a 1 kg body. It was moving with the 20 meter per second. A second body which is of 2 kg, which was moving with the 10 meter per second. They are moving in this direction. They are going to collide somewhere here, and they are again going to moving with 2 kg and 1 kg. What we don't know, it's their final velocity is required. It's a v1, it's a v2. So one of the approach was this, that you just remember the formula, apply the formula, and got the answer. Calculate the V1, calculate the V2, and so on. So the things will be done like this. Now second approach, that it is the same question. That means they have given that this is the elastic collision. This is the elastic collision that is mentioned. So when they mention elastic collision, now I understand that my coefficient of restitution would be equals to 1. So when elastic collision is there, I can conserve the momentum. Yes. So when I conserve the momentum, what I can write is the m1u1 plus m2u2, that should be is equals to m1v1 plus m2v2. So while writing this, this is 1 into 20 plus 2 into 10 should be equals to 1. It's a m1 into v1 plus 2 into v2. So from this, it's a 1 into 20, that is of 20, plus 2 into 10, it's a 20, should be equals to v1 plus 2v2. So this 20 plus 20, it's a 40, is equals to v1 plus 2v2. This is equals to 40. v1 plus 2v2, that would be equals to 40. Is it clear? Is it? Great. Now one more relation, that is equals to E is equals to velocity of separation. It's a v2 minus of v1 divided by velocity of approach. It's a u1 minus of u2. For elastic collision, this would be equals to 1. So v2 minus v1 I don't know, but I know u1 and u2 both. So I can have, it's a 20 minus of 10. So from this I am having a relation, it's a v2 minus v1 is equals to 20 minus 10, this is 10. So let's say this is relation number 2 and this is relation number 1. So let's just try to solve this, that how, what solutions do I have. Let's have a look, that this was our first relation, that was v1 plus 2v2 should be equals to 40, and the second relation was minus of v1 plus v2, that would be equals to 10. Yes, this is the relation, it's a v2 minus v1 is equals to 10. So this was the relation. Now if I add this, this 2 would be the cancel. This 2v2 plus 3v2, that is equals to 50. From this I can have this relation, it's a v2 that would be equals to 50 plus 3 meter per second. Is it clear? Is it? Now if I put the value of v2 in any one of the relation, let's put it in the second relation. The relation was v2 minus of v1, that would be equals to 10, and this v2 is equals to 50 by 3 minus of v1 is equals to 10. So this is 50 by 3 minus of 10, that should be equals to v1, and this v1 is equals to 50 minus 30 divided by 3, this is equals to 20 by 3 meter per second. So even this was the answer. And if you observe this, it's a v1 is equals to 20 by 3 and v2 is equals to 50 by 3. If you observe this relations, that look at this. So this was the cases when v1, let's have a look, it's a v1 was 20 by 3 by formula concept, and v2 was equal to 50 by 3. So these are the same options, these are the same answer that I achieved, that we must understood very, this is very common sense, that answer would be the same. So this is the approach, this is the second approach, that if you forget the formula, so this is pure logic, this is pure concept, and even with this approach we can have the answer. I hope this is clear. Is it clear? So if I am having this approach only, even then I can lend to the correct answers. I hope this is clear. Is it clear? Yes, so we have now two approach. One based on the formula, that use the formula and do your work, and the second one is the based on the pure logic. It's a pure concept. I hope this is clear. So you can go with any of them you chooses to, but first approach, that is the approach of formula, have certain restrictions on me. What are they? Let's have a look. You will feel it and you will understand it. Let's suppose the next question says that this is first body, mass 2 kg, moving with 20 meter per second in this direction, and this is the second body. It is moving in this direction. This is 1 kg and it is moving with speed of 10 meter per second. At a midpoint, at a certain distance here, they are going to collide. Let me redraw this. That at a certain instant they are going to collide, and even after collision, let's say that this one will be moving in this direction v, even this will moving in this direction v1. That I assumed. I don't know whether I have chosen the correct direction or not. I'm not sure for it, but let's suppose I understood that v2 would be moving in positive x direction after the collision. Even v1 will be moving in the positive x direction after the collision. So the question is that for elastic collision, find out final velocities. Find out final velocities v1 and v2. So this is the requirement. Now now the situation is, when we have derived this relations v1 and v2. Let's look at this. Yes, when we have derived this relation, yes, what the situation was that u1, that means the first object is moving in positive x direction, another object is moving in positive x direction, and then we have derived everything. Now in this situation, whatever the question I am having right now, it is the situation where both the objects are not moving in the same direction, but both the objects are moving in opposite direction and they are moving towards each other. So as I understand that momentum is a vector quantity, I need to I need to respect magnitude as well as direction both. And in those cases where when we derive the relations, the directions were same. Here the directions would be the different. So my relations could be a different. So now what could I do? Can I derive for this also? Can I? Then I must say no. What we need to do is we need to go with the approach. Yes. So what I understand is that first thing that is clear in my mind, it's a elastic collision. So I can say, so it's a p1 initial plus p2 initial, that should be is equals to p1 final plus p2 final. Yes, I am writing all this in vector. Yes, so what I can have is this is 2 into 20 I cap. It is moving in positive x direction. This is minus of 1 into 10. It's a minus of 1 into 10 I cap. Yes, minus has been written because it is moving in negative x direction. That should be equals to m1 into v1. That should be is equals to m1 into v1 plus m2 into v2. So if I solve this a little, it's at 40i, it's at 10i. So that should be is equals to 30i. That should be equals to mass 1, it's a 2 into v1 plus m2, it's a 1 into v2. I hope this is clear. One more thing, it's an elastic collision, and when it is an elastic collision, E would be equals to what? So I can have it's a E, that is the velocity of separation. This v2 and v1, I have assumed, I don't know, I have assumed that both are moving in the same direction, so their relative velocity of separation, their relative velocity of separation can be written as v2 minus of v1 divided by velocity of approach. Now look at this, their approach, it is moving in this direction, it is moving in this direction, so what I need to write is it's a u1 minus of u2. I hope you understand this. Yes, it's a relative velocity of approach. If you remember the relative velocity in one dimensions, we used to say that when two objects are moving in the same direction, for that relative quantity we are going to subtract it, but when two objects are moving in the opposite direction to each other, for their relative quantity we are going to add it. It is the same thing we are doing here. It's a v2 minus of v1 divided by u1 plus u2. Please do not commit a mistake over here. This is E. So what I can have, it's my first relation. The first relation is 30 I cap. It is equals to 2 into v1 plus 1 into v2. Yes, and the second relation that is equals to E is equals to v2 minus v1 divide by u1 plus u2. This is 1. v2 minus v1 I don't know. u1 plus u2, this is equals to 20 plus 10, this is 30. So I am having it's a v2 minus v1 that should be equals to 30. This is the relation number 2. This is the relation number 2. As this is in I cap, this is vector v1 and vector v2, but I understood that this is moving in the I cap only, so I can write like this. It is the 30 I cap that should be equals to 2 v1 I cap plus v2 I cap. So I am having one relation that 2 v1 plus v2 that should be equals to 30. This is my first relation. This was the second relation that it's a minus of v1 plus v2 that should be equals to 30. That would be the second relation. So let's just try to solve it. Multiply it with negative, so that this would be the positive, this would be negative, this would be the negative. I hope this is clear. So this v2 with v2 1, this is 2v1 plus v1 that is equals to 3v1, that would be equals to 0. So v1 is equals to 0. v1 is going to be 0, and when v1 is going to be 0, I understood that v2 would be equals to 30 meter per second. So the situation is this is going to be at rest. Well, this is moving in this direction. I hope this is clear. Is it clear? Is it clear that v1 is going to be at rest while v2 is moving in the positive x direction with the speed of 30 meter per second? Now how could I come to know, that this will moving in the positive x direction? Because this has been arrived in the positive. If let's suppose for understanding purpose only, that if I am having a certain value of v1 in negative and v2 in positive, then I must understood that v1 must be moving in this direction. I hope this is clear. So so this is the way by which we can have any questions while considering that momentum is a vector quantity, and when it is a vector quantity, we must respect it as a vector and not as a scalar. I hope this is clear. Yes, so we have a two approach, we have a two relations. Yes, always go for that. Yes, if both are moving in the same directions, and even after collision they are moving in the same direction, you can always go with the formula, no issues in that. But if they are not moving in the same direction, and or let's suppose you forget the formula, Then what I need to do is go with the approach. Yes, when and when they have said that it is the elastic collision, when and when they have said that it is the elastic collision, you can always consider that. You can always consider that first, momentum is going to be conserved everywhere, and second, go with the coefficient of restitution. You would be having a two relations, you would be having a two unknowns. So with the help of two unknowns and with the help of two relations, you can solve that two unknowns. I hope this is clear. Is it clear? So let's just wind it up the session over here. This is the part 1. This is the very initial part of the collision. What I want is you just go through this, revise it, and have a command over this much session, because this is the basics and this are required. So you just have a command over it, and we will be back with the collision part 2 and onwards. I hope this is clear. Thank you. Have a good day. Take care. Bye bye.